Let's start with today's lecture. The title of this lecture is Analysis of Equilibrium. First of all, let's define the state of equilibrium. The state of rest in an appropriate inertial frame of a system of particles and or rigid bodies is called equilibrium. You may recall that inertial frames are set of observers or reference frames which are with respect to which are at rest with respect to each other, or at most they are in uniform motion along a straight line as seen from each other. So, when a system consisting of particles or particles and rigid bodies or only rigid bodies is at rest in a suitable inertial frame, then we call that the system is in equilibrium. What are the conditions which ensure this state of equilibrium? We will go in a very systematic manner. First of all, we will consider the equilibrium of a particle, a single particle. By definition, particle is a zero-dimensional body, that is, it has no length, breadth, thickness, etc., or no diameter. So, geometrically it is a single point. So, when this single point or a particle is subjected to several forces, naturally all the forces must meet at the particle. They are concurrent forces. So, we can say that the conditions of equilibrium of a particle are same as the conditions of equilibrium of concurrent forces. So, suppose F1, F2, F3 up to Fn are force vectors which are passing through the same point as shown over here. This is the location of the particle and all the forces F1, F2, up to Fn are meeting here. Then the resultant force Fr is the vector sum of all these individual forces. This resultant force should be equal to 0 for the state of equilibrium. In the component form, the same condition can be written as the x components of all the forces when summed together they are equal to 0, y components of all the forces summed together gives you 0, and similarly z components summed together is 0. Next, we go to the equilibrium of a single rigid body. Now, the forces are no longer concurrent forces, they may be acting at different points. Suppose here is a anyway, let us say the forces are passing through different points of the body, then the conditions of equilibrium are sum of all these individual forces equal to the resultant force Fr is equal to 0, and besides this we require another set of conditions, that the moments of all these applied forces taken about any arbitrary point O is the resultant moment is also equal to 0. Now, suppose I consider the ith force. Let us say here are different forces acting on the body. I choose an arbitrary point O in space. So, the position vectors, if I draw the position vectors of an arbitrary point, let us say on the force F1, F2, etc., the position vectors are vector R1, R2 up to Rn. So, the moments of, let us say, the force F1 about O is R1 crossed with F1. Similarly, for the F2, R2 crossed with F2, etc., up to Rn crossed with Fn. So these are the first set of terms are the moments of forces about point O. The second set of terms is the moments of couples. Couples are, you may recall, they are free vectors. So the rigid body may also be subjected to some individual couples. So the moments of these couples when summed together are given by the second term, that is summation of Ci. So the resultant moment consisting of moment of forces and moment of couples should be equal to 0. So for the equilibrium of a rigid body, these two conditions must be simultaneously satisfied. Well, these vector conditions can be easily written in the component form also. For example, sum of all the x components of resultant forces is equal to 0, y components of forces, etc. And similarly, for the resultant moment, the x component or resultant moment is individually 0, y component is individually 0, etc. Well, I have stated that we can choose any point O for taking the moment of forces. Suppose I choose another point O dash. For example, here is point O which was chosen arbitrarily, another point O dash is chosen. Let us